Welcome to qnawire.
Hello everyone, this is the solution to problem 10 of chapter 24 of college physics. So here first we're asked to find what the direction of the induced electric field is due to a changing uniform magnetic field in various directions. So for part A, the magnetic field is pointing from the south to the north direction, which is indicated by the green arrows over here. And we're told that the magnetic field is increasing in this direction. So that's what I've indicated here with this delta B arrow over here, which is just to remind us that the field is increasing in the same direction as the field is pointing. So then what we want is for the induced electric field to be such that it generates a magnetic field that opposes this motion. So to oppose this motion, we want the induced magnetic field on the top to be pointing down opposite the direction of this guy, because this means that, let's say that you have a north pole over here on the top, then you want a north pole on the induced magnetic field pointing down so that the two north poles repel each other. So then this is using your right hand rule over here, you can see that the induced electric field has to curl around in this direction. If it does, then the induced electric field is going to have an induced magnetic field that is pointing downwards, opposing the motion of the change in the field, in the original magnetic field. So then what's the situation in the bottom? Well, in the bottom here, you have a south pole. So in order to stop the motion, you want a north pole over here as well. And that's because the north pole that you induce is going to attract the south pole of the change. So in order to do that, you need your electric field to go around this way. So you want E to point this way, go around in a counterclockwise direction if you're looking at it from the top, such that the induced field on the bottom is also pointing up. So this is again the induced magnetic field. This is part A. For part B, you have basically the opposite situation, and it's also rotated by 90 degrees. So here what's happening is that you have a magnetic field that is uniform and is pointing in the east to west direction, indicated by the green arrows over here, or the green field lines. But the change is in the opposite direction to the motion of the original field. And so that's what's indicated by this black arrow over here. So again, to oppose this motion, we want the induced magnetic fields by the induced electric fields. So these are the induced magnetic fields to be pointing on this side, on the west side, to be pointing to the east. On the east side to be pointing to the west direction, and on the west side to be pointing to the east direction. And again, the reason for this is clear. You imagine that the changing magnetic field has a north pole over here and a south pole over here. And so you want a north pole over here to attract the south pole, and you want a north pole here to repel the north pole. And so if you use the right-hand rule again, then you will see that in order to induce these magnetic fields, the induced electric fields have to be pointing clockwise on the bottom and counterclockwise on the top, or clockwise on the west and clockwise on the east and counterclockwise on the west sides of the magnetic field. And then finally, we're asked to find out, or to do the same drawings for when the magnetic field is changing at twice the rate. Now, what I've shown here is that the direction in both cases do not change. It's the same direction as you had in parts A and B before. But the electric field is going to be twice as strong And the reason for that is that if you assume that there is some coil of wire over here, for example, that has some typical resistance R, then the induced EMF is going to be given by this formula. Now, for the first rate, you're going to have that epsilon F is the induced EMF is going to be given by this expression over here. For the second scenario, the same change occurs in half the time. So that's why you have this factor of a half delta T over here. And the flux doesn't change. So it's the same, or rather it's the same change in flux as before, but now occurring at twice its rate. And so the induced EMF is going to be twice the original induced EMF, which if you imagine being given by some current running in the loop, you're going to find that it is actually twice the current that you had in the initial case. And that corresponds to an electric field that is twice as strong. So what I've done to indicate that is double the lines on each side of all the diagrams. And so that